Hello there. Review the acid-base questions that we had. So you already did those, but let's remind ourselves what is Arrhenius theory. So the Arrhenius theory is acids which release protons in the water. So proton releases in water is called acids based on the Arrhenius theory. Example is hydrochloric acid. It releases H plus. So the Cl minus there, but well, the more important thing is protons are released to the water. So what's a base? Hydroxides released to the water. So that's something like sodium hydroxide releases OH minus to the water. So that's how the Arrhenius theory, the oldest theory for acid base. Next one is Bronsted and Lowry. So the Bronsted and Lowry actually explains without the water, right? So even with the water doesn't matter. So the proton donors are acids, which is ammonium plus has a proton to donate, and H3O plus has a proton to donate. So therefore NH4 plus and H3O plus are acids. Now, who are the Bronsted Lowry bases? Proton acceptors. Who accepts? Ammonia accepts a proton. Water accepts a proton. So therefore ammonia and water is Bronsted Lowry bases, right? So the two sides of it, right? So acids are NH4 plus and H3O plus, bases are NH3 and water. The very important two pieces, two species of chemicals, right? Now the Lewis definition, not all of you need it, but if you really need it, depending on your course, what's a Lewis acid? The electron pair acceptor is a Lewis acid. It's kind of called La, Lewis acid. Lewis acid accepts La, right? So the aluminum chloride accepts a chloride lone electron pair from chloride. That's why it's an acid. So electron pair donors, in this case actually chloride is the electron pair donor. So that's the Lewis base. Okay, so just know the two theories, Arrhenius and Lowry Bronsted, right? Okay. Now the other thing you just somebody asked me too. So strong acids. What's a strong acid? HCl, HBr, HI, sulfuric nitric. So they dissociate 100% and H plus to the anions, right? Strong bases, KOH, sodium hydroxide, calcium hydroxide, barium hydroxide, and so on. So they will dissociate 100% to OH minus and to metal cation. But these ones don't have a problem. The problems are with the weak acids and weak bases, right? So the weak acids have a double arrow because they are dissociating. The dissociation is less than 1%. So therefore, that's why. You can also add the water, right, to make H3O plus in case. But always I would see it as HA, H plus A minus, and I stable, M and 0 0 at the beginning, minus x goes to xx, and then when you have H plus in the product side, you write a Ka, product over reactants, and then you write those products and reactants, and it's x and x at the equilibrium. So that's x squared divided by m. So this is the format for every question for weak acids and bases, right? So just to go back and rewrite it so you can know how to do the weak acids and base questions. Now, so calculate the molarity of Methanoics. That's an HA to me, right? And you're looking for calculating molarity. You're given pH, you're given Ka, right? So the Ka value given, so we know it's a weak acid. It's an HA. Pretty simple, right? So HA goes to H plus and A minus, and I stable, right? Or I stable. And M goes to 0 0 at initially, and changes are minus x x x, and equilibrium is M minus x x x, but this x is negligible, and Ka because of the H plus. So product over reactants, let's write that, and you get x squared over M, which is the initial equilibrium line molarities for the products over reactants. Right now we're going to use the pH given 3.27 to convert to H plus. The H plus is actually X, right? So 10 to the minus pH, that's how you go from pH to the H plus. That is actually X. That is getting us 5.37 10 to the minus 4. and know how to use the calculator. Otherwise, ask me. We can show you. Now you plug into the x squared, so Ka is x squared m, cross multiplication here, and you get m is x squared over Ka. We need m, so therefore 5.37 10 to the minus 4 squared divided by the Ka, and then yeah, plug and chug, right? So we should be getting, let's see what do we get. Yes, so 1.6 10 to the minus um, 3. So that's it. Oh, actually, we should write the methanoic acid. It's a good idea. Let's write the methanoic acid. So in case, right? So because you have already done your organic chemistry part. So HC double bond OH. So I call the HCO, right? And that one is actually CH2O2, sometimes written like that, but it's an HA for the math problem, right? For calculations. Now this one, you are looking for Ka, you're given carboxylic acid, carboxylic acid actually, and its monoprotic molarity is given and the pH is given. When the pH is given, we're going to convert that to X, right? Now, this one also I would think HA, H plus A minus I stable, right? Initially 0.06 molar, nothing, minus X, and the zero point zero 0.06 minus X. That's equilibrium. This X is negligible because it's very small. And the Ka written because of the H plus in the product side, write the product over reactant, X and X at the equilibrium, and then divided those two and divided by 0.06, right? And that's the molarity. So x squared over zero point zero 0.06, yes, and then we get the x from the pH. H plus is equal to 10 to the minus pH, plug in minus 3.57, and plug into the calculator, right? So make sure you have a bracket 10 to the power minus 3.67, right? And we should get, okay, 2.7 10 to the minus 4, and we plug into the x, so, and square it, right? So 2.7 10 to the minus 4 squared divided by 0.06. That's it. So that's the Ka, and you can actually look it up. If you don't know what it is, you can look it up in a data sheet too, right? What's the name for it? But we know we are given carbolic, right? It's just a monoprotic acid. But if you know that if you're done organic again, it's phenol actually. Phenol looks like this, benzene and the OH. And remember, this OH is not a base, right? This breaks into O minus and H plus. That's why it acts like an acid, weak acid. So not a base, because to be a base, you need a metal cation, right? Okay. The next question. Yes, you are given HCN, molarity given, and you're looking for pH and Ka given. Voila, same style. It is an HA, go to H plus A minus, right? And HCN, actually, it's good to know HCN dissociate into H plus and Cn minus. Leave it aside. We do the math the same style. So 0.500 minus XXX, zero point 0.5 minus XX, this X is negligible. Product side H plus, it's a Ka. Product over reactants, plug in equilibrium concentrations, H plus A minus divided by HA, that is X squared actually. At the equilibrium, you have XX, so divided by the molarity, zero point 0.5. And now, so we can plug in the Ka is X squared over 0.5, and yes, let's do the cross multiplication and take the root because we need the X, right? So now root of the Ka 0.5. So let's do the math here. Make sure you have a bracket there when you use the T84, and there you go. So let's take the root of this value. Okay, we're getting, yes, X is, yeah, that is H plus actually. H plus is 1.76 10 to the minus 5 molarity. So you look for the pH then, minus log of that value, right? So that'll give me, let me see, 4.75, it's a weak acid. That's what we thought. HCN is a weak acid, and Ka value is reasonable, so we are good, right? The Ka is product over reactant, H plus Cn minus divided by HCN. It's good to know this writing because there could be multiple choice questions with this one. If you have water, you can add water there for the equation, but not for the expression. Expression, because water liquid don't go to the expression. But X plus and the H plus could be H3O plus, right? So those are the little variations you can have it in your exam. So just a reminder. Okay. Next one. So unknown 0.35 molar solution, pH is given, calculate the Ka. Same style. So just do it for homework, right? We skip that one. So let's go to the other one because this is something important I want to show. It's a weak base, so any weak base behave the same way, but we'll work on ammonia. It's an important one to know. Ammonia plus water, this lone pair actually grabs a proton from the water. Water is the acid, see, it gives the proton away, so ammonia becomes ammonium and hydroxide ion. So then you do the normalized table, 2 molar 0 0 minus x x x and 2 minus x x x, right? Okay, now this is the magic. OH gives you Kb, and this X is neglected, and then Kb is product over reactants. Let's write them. Expression is ammonium OH minus divided by ammonia, right? Okay, so that's the key point to understand. Any weak base, RNH2, anything, you write it that way. Plug in the Kb because we wrote the Kb already. There is OH, make sure, and then cross multiplication here, you get 2 times 1.8 10 to the minus 5 x squared. Take the root of both sides, you get x. Now the magic still, the x is actually OH minus, right? So now let's get this value calculated first. Yeah, that gives me actually pOH, which is minus log of this value, the OH concentration, 3.6 10 to the minus 5. Yeah, that gets you the value of how much? Let's see, 4.4. That's if you are looking for pH. So that means we need the pH is 14 minus pOH. So that gives me the value of 9.55. Weak bases are around 910. Voila. Thank you.